So today's lecture is on ordinary least squares. And we'll have two lectures on this. The second lecture will be a little bit more practical, and this one will just sort of cover some of the principles and some examples of this. And there's some nice companion reading here. So we saw in the last lecture how to do hypothesis tests, but hypothesis tests don't give us any predictive power. Like if we want to use a numerical model to predict an outcome, having a hypothesis test it doesn't help us at all with that. So that's where regression comes in. So we're going to basically cover the nomenclature today, talk about the model equation and how noise or statistical error comes in. And we'll see some examples in one and n dimensions. And I think the key, or one of the key concepts, will be connecting regression with probability distributions here. And we'll see how you can also do hypothesis tests and confidence intervals in linear regression, which is what, the other two topics we covered in statistics so far. So let's take a look at the one-dimensional regression. So Unit 12, this unit has many lectures and they cover many different situations like one dimension, n dimension, linear, nonlinear, regression with noise, regression with discrete variables. We won't cover all of them this year, but you can definitely look up whatever you need if you're doing a regression in the lecture notes. So we're going to see basically the following setup. We have x, which is always going to be our independent variable. X is sort of like the description or the features of your problem. So if it's like a chemical reaction, x might be the temperature and pressure, and y might be the reaction rate. So y is the labels or the measured variable or the dependent variable. And in this example, we want to fit a line to it. So we have here that we are going to have y equals alpha plus beta x. So this is an intercept, and this is the slope. So if we have a hat, that means it's an estimate, okay? So we have x and y, which are true, so they don't have hats on them. So like the x's are real things that we have. This model, this equation here is a model for what we think y should be. So in reality, the real y's are coming from an alpha plus beta x plus some error. So that is, we assume, I mean this, it may be the case, but in general, we cannot reproduce the y's exactly. That is, our x's and y's are made up of some true alpha, beta, and then there's some epsilon. So what this means in practice is that our y's typically don't lie on a perfect line. Like that never happens in the real data that lies perfectly on a line. So the way we account for the fact that it's not on a line is we add this extra little wiggle term epsilon, and this says there is some noise that causes our data not to lie on a line. Now we're going to assume, this is an assumption, that how our data deviates from a perfect line is coming from a null distribution. Now we'll talk later about how to test that assumption. We usually test it after we fit our equation. But this means that our data is basically deviating from this perfect linear equation by a normal distribution. And that assumption, remember, is valid because the central limit theorem tells us that in many natural processes, a bunch of noise terms, when added together, create a normal distribution. Okay? So here is our model equation. We believe that the y's are coming from an alpha plus beta x plus some noise. And we will fit this equation here. Okay. So this, we're not going to go over all of this here, but this is basically describing all of the terms that we have here. So let's see an example for one dimension. Okay. So remember that our y hats are basically our estimate. And then the y's without the hat are the true. So mathematically, we want our y minus y hat to be as small as possible. That means we want our estimated y's to be as close as possible to the actual y's. So if this is our objective, to minimize the distance between the y's and the y hats, then what can we change? Well, what we can change is alpha and beta. So we're going to change our slope and our intercept until our y's are as close as possible to our y hats. So one of the things we need to do is basically we rewrite this all in terms of our alpha hat and beta hat. So we're basically saying we have a function here, and that function is we have an input, an alpha hat and a beta hat. Remember, we are handed our x's and y's, so those aren't things we can change. The only thing we can change is our estimated intercept and our estimated slope. So as we change our estimated intercept and our estimated slope, that changes how close our y is to the y hats. And now notice I've just substituted in for y hat our y in for y hat, I substitute the definition of y hat because remember that y hat is defined by this. Okay. So you can basically take this equation and you could use any minimization technique. Like you can take the derivative with respect to alpha, set it equal to 0 to find the minimum, or you could take and then take the derivative with respect to beta and set it equal to 0. You can show that if you do that, that the beta hat, the optimum, is given by this equation here. Okay? This is kind of an interesting equation because you'll notice that this term up here is basically the covariance of x with y. And this term down here is the standard deviation of x with itself. It's kind of interesting that it comes out that way. So we can write that more compactly. So beta hat is equal to the covariance of x with y divided by the standard deviation of x. And then for the alpha hat, you can show that it's basically the average distance between the true y's and the beta hat times xi. Okay. So let's go ahead and see an example. Actually, before we go on, are there any questions on this derivation here? Okay. So let's see an example. So this code here, just you can ignore this. It's just me making some data. Okay, so this is just me generating random data. So this has nothing to do with linear regression. Okay, so I've generated some random data. And if you look at the code, you can see that the true slope is 2.5 and the true intercept is 1. Okay, so the true slope is 2.5 and the true intercept is 1. Now this is how we compute the regression. We first get the covariance matrix because the covariance matrix will contain on the off diagonal the xy covariance, and then on the diagonal in the first element it will contain the standard deviation of x. Okay, so we have covariance of x with y with itself. Now there's one change here, and that is that the deducted degrees of freedom is equal to 2 here. Okay, the deducted degrees of freedom is equal to 2. And the reason for this, well, actually, we don't really need to get into it because they cancel out, right? So the deducted degrees of freedom will cancel out in this expression. We'll talk more about why that is, why we have deducted degrees of freedom as 2 in a minute. But for this expression, it doesn't matter because it cancels out. But we'll talk about that more. So why does it cancel out? Because you have the 1 over n minus 2 in the numerator, and you have the 1 over n minus 2 in the denominator, so they cancel out. But we'll talk more about why that matters later on. But for now, for computing beta, it doesn't matter. And then here's how we compute alpha. Okay, so then the alpha we get is 0.79. Remember I said that the true alpha was 1, and the slope, or the intercept, sorry, that was the intercept. The slope is 2.5, and the true intercept was 2.5. Now, why do we get the wrong answer for the intercept, right? Why do we get 0.79 when the true one is 1? Well, it's because this is a random variable, right? Alpha hat is a random variable. We sampled, we have random noise in our y. So because there's random noise in our y, the alpha, which is a function of the y's, is also a random variable. And our betas is also a random variable. Now we'll talk in a minute. In principle, the probability of seeing an alpha hat should be centered at the true alpha. That is, the most likely alpha hat we see is 1. But of course, this is a random variable, so it's not, you don't always see exactly the most likely outcome. In this case, it did match. Okay? So remember, alpha hat is a random variable because it's coming from the y's, which have that plus epsilon term, so they themselves are random variables. Now here I'm plotting my best fit line. Okay, so I'm plotting x. Remember, x is always constant. We always assume there's no noise in x. X is just some true known thing. It's the y's that have the randomness. So x is always true, it's always given. Then here is my y uh, line. So these are my y hats. So it's alpha hat plus beta hat times x. Okay, and then that's my regression, that's my best fit line. So are there any questions about this example? Okay. So remember that we started this by saying we assume that our noise is random. So we can test that after we have our y hats, because in principle, the y minus y hat should be normally distributed. So the first thing is that we don't actually have a hypothesis test yet for testing if something is normally distributed. So that's where we're going to use something called the Shapiro-Wilk test. There are multiple uh, tests for normality. Shapiro-Wilkes is just a reasonable one to use. I think it's one of the better tests for normality. But this one is a little bit different, okay? So we're saying that the null hypothesis is that the data is normal. So usually when we've done hypothesis tests, we've always kind of been interested in disproving the null hypothesis, right? But here, we kind of want the null hypothesis to be accepted. We don't want to reject it. So that is testing to see if the data is normal, okay? So we want the null hypothesis to be true here, right? If we want to justify our regression, then we want a p-value greater than 0.05. Okay, this is just showing you how to use the Shapiro test. You call it from Skippy stats, and you just put in a list or an array, and it gives you, I think this code example is out of date. I think it tells you which is the p-value. I think the p-value is the second number. Yes. So I think in the current Skippy stats, I'll have to check. Maybe I can check right now. No, it still does this. Okay, so the second number is the p-value. All right. So just something to remember. The second number is the p-value. Okay, so here's an example here where the p-value is 0.002. So this is not normally distributed data. So here, what I did is I took the numbers 0 to 1, equally spaced, and that's not normal. Obviously, that's not normal because the numbers 0 to 1 are not, they're not centered around some, some mean value. Okay. Okay, so let's use this new hypothesis. Actually, before I go on, does anybody have any questions about the Shapiro-Wilkes hypothesis test? Okay. So let's go ahead and use this test. So after doing the regression, we want to check our assumption that the data was normally distributed. So epsilon is equal to y minus y hat. So we can check the values of epsilon and see if they are normally distributed. So one of the first things we can do is we could just histogram it. And by the way, epsilon, these are called the residuals. The residuals, that is the residual error after estimating our y with y hat. So if we histogram them, this gives us one way to look and see are they normal. Okay? So, I mean, looking at this, that they should be centered at 0 and be normally distributed. These aren't really great. Like I would not say looking at this, I can say yes or no, it's normal. But we can use the Shapiro-Wilk test, and we see that the p-value is 0.17. So this tells us that there is not sufficient evidence that they are not normal. So the default assumption is that they are normal, and that is maintained. So that's one of the ways we can justify a linear regression. So thus far we've seen two ways to look at a linear regression. We can plot it, which I think is always the most important way to assess a regression, is plotting it. Then the second way to assess a regression is to show that the residuals are normally distributed using a hypothesis test. Okay? So another way that people use to assess regression is something called goodness of fit. Okay. And goodness of fit is basically the ratio of the sum of squared residuals. So we have a sum of squared residuals divided divided by the total sum of squares, which is total sum of squares is like the standard deviation of y without the 1 over n. Okay. Now then we do 1 minus that because we want the goodness of fit to be close to 1 when it's a good fit and close to 0 when it's a bad fit. So the whole idea of this measure is that by doing this SSR, which tells you how close you are to y hat or to y, right? This is assessing your residuals. Dividing it by the TSS makes it so that this number is bound between 0 and 1. So when it's 0, that means basically you have terrible fit, like your fit this number here is basically 1 relative to the total sum of squares. And then when you have a very good fit, this number, the numerator is 0, so this becomes 1. And it turns out that we had learned correlation coefficient. Remember we had seen correlation coefficient in Unit 7? The reason why this is called r squared is that the square root of this is the same as correlation coefficient. But the difference is that, right, if you take the square root, you only get the positive value. So goodness of fit doesn't tell you about the direction, right? So you could have something that is negatively correlated or positively correlated, right? Doesn't tell you anything about that. But the r squared, if you take the square root, it should be the same as the correlation coefficient. So goodness of fit is another way to assess a linear regression. So we've seen 3 ways so far. We've seen plotting it, the residuals, the hypothesis test for normality, making sure the residuals are normal, and then looking at goodness of fit. So this is just showing you how to compute goodness of fit. The SSR is basically y minus y hat squared, summing it up. And the TSS is basically y minus the average y, summing it up, scoring it. And this gives us our r squared. So here I have the r squared, so it's 0.945. Then I took the square root and I get 0.97. And then down here I'm showing you if you look at the correlation matrix, which is what we had seen in Unit 7, we see the same number, right? So correlation coefficient and the goodness of fit are the same. Now notice correlation coefficient doesn't require you to do a regression to get. The goodness of fit requires you to do a regression and then you compute it. Correlation coefficient is something you just do without doing a regression. All right. So are there any questions on goodness of fit and these ways to assess our linear regression in one dimension? Okay. So I think goodness of fit is actually not a very effective way to measure a linear regression. I mean, everybody does it. You know, if you go to Excel and you do like fit best fit line and you get your r squared and it's like 0.97, you know, you think I did a good job. But um, there's no real, benchmark. Like if you have a r squared of 0.82, is that good or bad? It's unclear, right? Just like we saw in the correlation coefficient lecture, it doesn't really help you. Now, can anyone tell me what is a way to assess correlation that we learned that does have a standard? Like we learned a way to assess correlation that gave us a yes/no answer. What was that method? Does anyone remember? So we saw correlation coefficient, and we just saw this goodness of fit. What was a way we learned in this class to assess a correlation that gave us a yes/no answer?
Is it covariance?
No, not quite.
Correlation test.
That's right. The Spearman correlation test, which is a hypothesis test. So the Spearman correlation test gave us a p-value, right? So that gave us the ability to reject a null hypothesis. So far, the only thing we've seen that gives us an actual sort of yes/no answer was the Spearman correlation test because it gave us a p-value and then we can reject or accept based on the p-value. So I would say I would avoid goodness of fit. I just want you guys to know because many people use it. But if you are going to do a goodness of fit, you might as well just do a Spearman correlation test. That way you can have an actual p-value. All right, but now we're going to go a little bit deeper. So Now we're going to do a little bit of uncertainty analysis or error analysis. So we're going to try to do hypothesis tests and confidence intervals. And confidence intervals and hypothesis tests require you to have a standard error. So let's go ahead and get standard error. Okay, so this is just kind of a review on what standard error is. So we're going to use, I know we had used sigma e before, but we're going to use, I think we're going to, no, we're not going to use sigma e. We're going to use sigma with a little subscript indicating the variable of interest. Okay. So once we have standard errors, everything will follow a t-distribution, where the t-distribution is centered at x bar minus mu, where mu is like our true value, and x bar is our estimate divided by standard error. So we're going to see a whole bunch of examples where we're going to get standard error of intercept, standard error of slope, standard error of different variables of regression, standard error of the residuals. And then once we have a standard error, so once I show you how to compute the standard error, then you can assume a t-distribution and do any kind of confidence intervals or hypothesis tests. So the name of the game is to get a standard error, and then you can use t-distribution and use the tools we've learned in the past about hypothesis tests and about confidence intervals. And then just like normal, that if you're looking at something where the n is greater than 25, you can use a normal distribution. If n is less than 25, you can use a t-distribution. Now there's one kind of trick here, is that this n here is not exactly the number of data points. It's going to be n minus the number of dimensions in x plus 1. Sorry, it's confusing. N minus d, the deducted degrees of freedom. So it's going to be n minus d, where d is the number of the number of coefficients we're fitting. So for one-dimensional linear regression, the degrees of freedom is n minus 2 because we're fitting a slope and intercept. Now this kind of makes sense because remember when we used the t-distribution in the past, it was n minus 1, right? Like whenever we use the t-distribution, if you had like 7 data points in your sample, the degrees of freedom in the t-distribution was 6. Now the degrees of freedom in the t-distribution will be equal to n minus the number of coefficients you have. So if we have a slope and an intercept, it's n minus 2. We're going to see some n-dimensional regression in a moment, and there it might be n minus 3, n minus 4, n minus 5, depending on the dimensionality of the problem. Okay. So, okay, now we do use S. Okay, so here's the standard error equations. I usually write them as S squared, just for convenience. So the standard error in the residuals squared is equal to 1 over n minus d times the sum of the squared residuals. We don't usually use the standard error in epsilon, but it's used for other expressions. So once you have it, you can get the standard error in alpha, the intercept. So the standard error in the intercept is equal to this expression here, which is a function of the standard error in the residuals, and the standard error in the slope is here. Okay. So I want to make sure that we're getting this, is that alpha and beta, those are random variables because we compute them depending on y, and y is a random variable, right? So computing alpha is a random variable, right? Like we saw before, we had computed alpha for our example and it was 0.79 when the true alpha is 1. And if we had regenerated new random y's, we would have got maybe 1.05 for alpha. And if we did it again, maybe we would have gotten 1.2 for alpha. It's a random variable. So that distribution it comes from a t-distribution centered at 1 and with a standard error given by this equation. Okay. Now, why is it a t-distribution? Why isn't it a normal distribution? Because we're estimating both the standard error, like we don't know the standard error of alpha. I'm estimating it using this expression. So we're estimating both the standard error and the random variable itself. We're estimating both alpha and its standard error. So that's why it's a t-distribution. Remember that when we learned in the central limit theorem lesson? We learned that if we knew the population standard deviation, then everything was normal. But if we were estimating both the population standard deviation and the population mean, then we had to use a t-distribution because we had to correct for the fact that we're estimating both things. The same thing's happening here. We're trying to find alpha and we're trying to find its standard error. Okay, that's the same thing as like the population standard deviation. We're just using the word standard error here because it depends on more than just the standard deviation. It depends on also the values. Okay, so that means that our alpha hat is coming from a probability distribution, and our beta hat is coming from a probability distribution. And these are coming from t-distributions whose parameters are this standard error given by this one and this one. Okay, so before I go on, I think it's really important that you understand this. So are there any questions on this? Any questions on how these alphas and betas are random variables who are coming from t-distributions? Are there any questions on that?
Are we going to go over examples of using this?
Yeah, we're going to see some examples of how to use this in a moment.
Okay.
Okay, so here's an example. Good. Okay, so here we're going to compute the standard error of the intercept, and then we're going to show the probability distribution. Okay, so here are the steps. So the first thing I do is I put down what are the degrees of freedom. So remember that, sorry, this is continuing on the linear regression I showed above, right? I had the linear regression we had above. So that's where these variables are coming from. The first thing is the degrees of freedom. So in that linear regression, I was computing a slope and an intercept. So we take -2. So this is the number of data points, then we subtract 2. Here I compute the standard error squared in the residuals. So this is just using the equation I have above. Then here I compute the standard error in the intercept using the equation above. So in the standard error for the intercept, remember I have to take the square root of this. So the standard error in the intercept is 0.84. Okay. So, what does this mean? It means that the intercept is coming from a t-distribution whose, standard or whose distributed according to a 0.84 standard deviation. Okay, so let's go ahead and plot that. So what I just said is that the probability of seeing any particular alpha is coming from a t-distribution centered at alpha hat. That is the alpha we computed. It's the standard deviation of this t-distribution is the standard error of alpha. And remember, the t-distribution takes in 3 parameters. The other parameter is the degrees of freedom. So here is a plot, okay? So this plot, the blue line here, this is that probability distribution of alpha, okay? Now I'm showing you in red where the true alpha is. Remember, our alpha that we computed was 0.79. And this is showing you where the true alpha was. This is the one we didn't see, right? This is the one that we were trying to estimate. And you can see that it fell pretty close to what we estimated. Now we have this probability distribution, right? We have now this probability distribution here, so we could do things like compute a confidence interval, right? We could compute a confidence interval of where the true alpha lies. And it looks like if we were going to build like a 95% confidence interval, that the true alpha would lie within it. So that's a good sign, right? Other things we could do with this probability distribution, we can do hypothesis tests. We'll see that in a little while. But so I think the key thing from this example is that we have, right? We said at the regression that our alpha is a random variable. It depends on what our y's are. And here I'm showing you the distribution of that alpha. I'm showing you the probability distribution of alpha. Okay, so are there any questions so far? Okay. So now let's go ahead and construct a 95% confidence interval. Okay. So, I've computed in this example here, I computed the intercept to be 0.79. And if you were to tell someone, that the interval is, or that the slope or the intercept is 0.79, you can do better, right? You can do it's 0.79 plus or minus 0.2 or something like that, right? So we can give a confidence interval for the parameters. And that's kind of useful because sometimes people want to use the slope or intercept in other calculations. So if you can give them a confidence interval or an uncertainty with that number, that's really important. Like sometimes we want to maybe compute, I don't know, the free energy of solvation. So we do a couple experiments at different points, then we do a regression. And then the slope is going to correspond to the free energy of solvation. So we can now get confidence intervals for the slope from our regression. Okay, so now this is about the slope. So we're going to be using the standard error and beta. Okay, so remember for computing a confidence interval, that it's going to be basically our estimate plus or minus a t or a z value times the standard error. And the way we find that t value is that we get it from, we have like if we do a 95% confidence interval, we have a specific t-value. If we do a 90% confidence interval, it's a specific t-value. If it's a 99% confidence interval, it's a specific t-value, right? So we just have to look that up, what t-value we want using the PPF function. So here is the way to compute the standard error in beta. Okay, the standard error in the slope. Then here I look up the t-value I want. So I'm doing a 95% confidence interval. So recall that we use the 0.975 because it's a double-sided interval. We have to get the 0.975 t-value. And then I have to put in for the t, to get the t-value, I have to put in the degrees of freedom. So then my slope is going to be 2.51 plus or minus t times the square root, right? Because I computed this as the square, so I've taken the square root. T times the square, or t times the standard error. So it's 2.5 plus or minus basically 0.3. So this, I can now say that the slope is 2.5 plus or minus 0.3 with 95% confidence. So we have now computed our regression, and we have given confidence intervals for regressed parameters. And it's not, this is the same kind of thing that as the degrees of freedom gets larger and larger, we could use a z-value instead. Okay. So are there any questions on this example? Okay, so we've seen that this computing the standard error allows us to plot and think about the probability distribution for our parameters. Then we saw getting the standard error allows us to compute confidence intervals. Now the last thing we're going to do is look at hypothesis tests. Okay. Now what this is doing is this allows us to assess whether certain parameters are needed. One of the most common questions in doing linear regression is that should you have an intercept? Right? So if you guys have ever done like any kind of regression, you maybe have thought to yourself, should I have an intercept or not? I think in Excel, like for example, you can check a box saying I'm going to have on my best fit line, I'll have a slope or I'll have an intercept of 0 or it will fit the intercept. So you can actually construct this as a hypothesis test. So if we were going to do a hypothesis test, remember that the null hypothesis is always the simplest case. So the simplest case would be that the intercept is 0. Okay, so we're going to assume then the null hypothesis that our intercept is 0. Then we're going to do the math assuming that the null hypothesis is correct, and we're going to compute a p-value. So let's begin. So I'm going to say the null hypothesis is that the intercept is 0. Then we're going to compute the intercept. So we're going to compute the intercept from our data and see how likely are we to have just seen that alpha. Because remember, if the intercept is indeed 0, there's still a probability distribution, right? Like basically it's still a random process. So we could still see something that's like 0.02 or 0.05 or minus 0.02, but that's just random. The null hypothesis is that the true intercept is 0. So then what we can do is, under that null hypothesis, let's see what we got for alpha. And remember, our null hypothesis is that alpha is a random variable coming from a distribution centered at 0. Then what we can do is see how likely is it to have seen that alpha under the null hypothesis. So let's be more specific here. So we're saying that the alphas are coming from a distribution centered at 0, and it's a t distribution still. And obviously the standard deviation of that t distribution is coming from our S alpha, or standard error in alpha. But there's one trick here, is that the degrees of freedom, we're accepting the null hypothesis, right? Our default assumption is the null hypothesis. So the degrees of freedom is now n minus 1, because the only fit parameter is the slope, right? We're assuming that the intercept is 0, so this becomes n minus 1 now. Now, the fact that it's D is 1 or 2, it doesn't make that big of a difference. I'm being kind of pedantic here and making this correct. But, in most linear regressions, your n is like whatever, 20 or 30 or 50. So having 19 versus 18 or 49 versus 48, it's not that big of a deal. So I wouldn't stress too much about it. But if we want to be real careful, it should be 19. Okay, so if you guys remember when we did hypothesis tests, so remember for the hypothesis test, we construct an interval that's as extreme as our value. And then we take that'll be our p-value. Okay, so do I have a picture? I don't have a picture here, but you guys can basically think back to, maybe I can show you guys again. Do I never have a picture of it? So I guess it's not this inside value, but we're computing the area of the outside. Should get a picture of this. We're computing the area outside of this, so not this area, but the outside area. Okay. So in the lecture, I'm computing the inner area, then taking 1 minus that to get the outside area. So that's from minus t to t. So what is t? T is going to be our computed alpha. Remember, it's centered at 0, so we don't need to do alpha hat minus something, right? Because our assumption, our null hypothesis is that it's centered at 0. So it's just going to be alpha hat divided by the standard error. So I think, I had to spend a lot of words on this. I spent a lot of words on this, but the actual test is very simple. All you do is you compute your standard error of alpha, the intercept. Then you take the intercept divided by the standard error. So the value of the intercept divided by the standard error. I just did an absolute value just so I don't get my t-value flipped, because if your intercept is minus or positive, you'll need to flip the bounds of the integral. Then I just did 1 minus the integral from minus t to t, and that's my p-value. So in our example, we had an alpha of 0.79, and that gives us a t-value of 0.94, and then a p-value of 0.36. So that p-value means that there is not sufficient evidence to reject the null hypothesis. That is, our intercept is indistinguishable from 0. So if I go back to my picture, and I look at my picture, what that says is that there is not sufficient evidence to say that this line does not intercept at 0, 0. Now, if you're looking at this, like, you might look at this and say, hey, it looks like it's going to hit here, right? But the thing is, this is a best fit line, and there's some noise in this data. So, it could have hit here, right? There could be some other slope here. So I don't have sufficient evidence to say it doesn't hit that. Now, here's a weird thing about this. It's not a weird thing, but if you're to rerun this example multiple times, you will get different p-values because, right, they depend on your random data that you generated. So let's get back to this. So I have run this notebook a couple times, and sometimes my p-value is, 0.39, and then one time I got a p-value of 0.04. So, in this case with a 0.04, you can reject the null hypothesis. Okay, so all of that was to, I think I spent a lot of time describing it, but it's actually a very simple test. You just take your intercept divided by the standard error in the intercept, and then you just compute the area of the extreme interval, and that's your p-value. So that allows you to assess if the intercept is 0. It allows you to assess if the slope is 0, and you can use that to assess anything like that. Now, it can go, you can go farther too. Like, let's say you're doing, I don't know, let's say you have 2 temperature sensors. Maybe you have 2 temperature sensors in a reactor. And you want to know, are the temperature sensors measuring the same temperature? That is the temperature at one point the same as the other point? There, your null hypothesis would be that the slope is 1. That is, like, when T1 is 5 Kelvin, then T2 is 5 Kelvin. When T1 is 100 Kelvin, T2 is 100 Kelvin. So that you could start with a null hypothesis that your slope is 1. And then you could see, are they measuring something different by rejecting that null hypothesis? Maybe the slope's 1.2, right? The other temperature sensor is reading 20% higher. So this ability to do hypothesis tests in regression is a really powerful way to answer specific questions about your regression. Okay, so are there any questions on that? And any questions in general on one-dimensional regression? Okay, if not, we'll just take a short break, and then we'll go into n-dimensional regression. So let's just take a 3-minute break here, and then we'll get back to it. Okay, so now that we've had a short break, are there any questions on the first part of the lecture? No? All right, so let's move on then. So we're going to now look at multiple dimensions. So we're not going to see ever, and you really won't ever see regression where you have multi-dimensional y. You almost always have basically it never happens. So it's always x that can be multiple dimensions. So we're going to view x as a n by d matrix, where n is the number of xy pairs of data points, and d is the dimension of x. Okay. So if we assume that, then beta, our coefficients, is going to become a d-length column vector. Okay, so we'll have one coefficient for each x. And then our sort of model equation is going to be y equals x beta plus epsilon. And we're obviously going to find a beta hat here that gives us a best fit to the data. So again, you could use calculus to show that that the best fit beta is given by this. This is actually called a Penrose inverse or a pseudo inverse. It's just xtx inverse times xt. So this is just a little bit of matrix algebra. And there's a function in NumPy that computes this. It's called, I think, p inverse or something, pseudo inverse. So let's go ahead and see an example of this. Now, one thing I kind of glossed over is that in this equation, right, it may look like you can't have an intercept, but you actually can have an intercept by having one of your dimensions of x be all ones. Okay, so we'll see an example of that. So let's say I have here this equation. So I want, this is me telling you secretly this is what we're going to try to fit. Okay, so normally you don't know what your values are. I'm telling you secretly that we have, 3 plus 3x1 plus x2. Okay, so normally you're not given that information, but I'm telling you, as an aside, that's what we're trying to fit. So we're going to fit to this equation. So y hat equals beta naught plus beta 1 x1 plus beta 2 x2. Okay. Now, notice that this is a two-dimensional problem. There's an x1 and an x2, but we're going to put an intercept in here. Okay, so it's like it's a three-dimensional problem where your x3 here, the kind of hidden x3, is always 1. So that's how we view it, and that's how we do the analysis. Okay. So ignore this. This is just me creating the data. Okay, so just ignore this. Okay, so it's just me making the random variables. So here's what my X matrix looks like. The first column is all ones, right? That's gonna give me this beta naught. That's the intercept. So it's like I have a dimension of X that wasn't stated. I have my X1 and X2, but it's like I have a dimension of X that isn't stated. That's always 1. Then here is my x1 and here's my x2. Remember, x1 and x2 are given to us. It's deterministic. It's completely, there's no randomness about it. x1 and x2 are just known. Okay, and then we are given y's that we're fitting. And remember, the y's are coming from a random process, right? Because they have that epsilon term. Okay, so this is my matrix of x. So that's my x matrix. And this code here, this is kind of important, right? Because if you're doing a math problem, you will probably be given an array of x1s and an array of x2s, and you have to convert them into a matrix. So make sure that your matrix has n rows and d columns, and you can use this numpy column stack method to do that. Okay, so then let's go ahead and find our beta. So I use, like I said, there is a method in NumPy that does this for you, but I just wrote out the equation. This is just a way for us to practice our linear algebra in NumPy. So it's the inverse of x transpose times x. So notice I use the at symbol here because it's matrix multiplication. Then once you take the inverse, you multiply it by x transpose, and then you multiply it by y. And that gives us our beta hat. And remember that if you're, in principle, this beta hat should just have d dimensions. So you can check to make sure you got the equation right if your beta hat has d terms, and in our case 3. So this should be a column vector with 3 elements. So there's another shortcut here. So I told you there's the p inverse. This is an alternative shortcut. I don't know why it has this here, but it does. So this is another way to do it, is that in the linear algebra library, you can use LSTSQ, and you can put in your x and your y's. Oh, I know why. So if you do the p inverse, it gives you this term. Then you still have to multiply it by y. If you use the LSTSQ, then you give it your x and your y, and it gives you out the beta hats. Now notice I put this special symbol here. That means that this thing returns multiple things, and I just throw away the rest. I'm only keeping the first thing it returns. So this function returns a bunch of extra stuff. I throw away all the other stuff and only keep this first term. Okay. So now that we have our betas, we can compute x times beta to see our y's and estimate them. Okay. Now notice that our problem has an x1 and an x2 and a y hat. So we can't really plot. I mean, we could get a 3-dimensional plot and plot x1 versus x2 versus y. But it turns out that that only works if we only have 2 x's, right? If we have a 3-dimensional, if we have x1, x2, and x3, we can't plot on 4 dimensions. So what we usually do is we plot y versus y hat. And this is called a parity plot. So I'm not actually looking at the x dimensions. I actually don't care about the x dimensions. I'm only plotting basically my predictions versus what the true values are. So these are my predictions. These are the true values. So you can see here, like, these blue dots, these are the true y's plotted against our fit. If we were perfect, if our y's matched our y hats in every instance, then all these blue dots would lie along the line. That would mean that, like, if I predicted 2, it came out to be 2, so it would lie on the line there. If I predicted 6, it came out to be 6, it was on the line. So by plotting this y versus y hat, it allows us to assess how good we are at fitting them. And this is a great regression. This is a great regression because you're basically above and below the line about half the time. That means, your regression fits pretty well. Okay, so are there any questions on this regression so far? Can somebody just confirm that the Zoom meeting is still occurring and everyone can hear me?
I'll hear you.
Yeah.
Great, thank you. Okay, so that is how we visualize or plot our regression in multiple dimensions. Now we can use all the same techniques we saw before. We can histogram our residuals, and we can assess, their normality. We can compute goodness of fit, right? We can do all those same measurements we had previously. One thing I didn't mention is that we can't really do correlation coefficient because we have an x1 and an x2. So this is an example, like in your multiple dimensions, you can't just compute the correlation coefficient. So that's where the goodness of fit is an alternative that might be useful. Okay, so I'm just going to talk quickly about the error analysis. So the same thing happens as before, where we have an n minus d term. Now d here is 3 because we had 3 fit coefficients, beta 0, beta 1, beta 2. So if we want the standard error in the residuals, we have, again, this equation here. But now to get our standard error in the fit coefficients, we have this expression here. It's a matrix expression. So this standard error in epsilon, this is a scalar, but this is a matrix, okay? And we get back a square matrix from doing this calculation, right? But we only have d betas, we have d betas, so a d by d matrix. So we have to remember that only the diagonal elements are what we want, okay? So only the diagonal elements of this matrix are the standard errors. So for example, the top left diagonal is the standard error for beta 0. Then in our example of a 3 by 3, then the 1, 1 element in the matrix is the beta 1, and the 2, 2 is the element for beta 2. And everything else is the same. Again, if we're looking at the probability distribution of our beta minus beta hat, it's a t-distribution centered at 0. Notice I rewrote it. In the previous one, I wrote it as probability of beta is a t-distribution centered at beta hat. This is the same thing. Now I have a probability distribution of beta minus beta hat. It's a t-distribution centered at 0 with a standard deviation of the standard error of beta, and then the degrees of freedom is n minus d. And remember, in this example, d is 3, not 2, because we fit 3 coefficients. Okay. So are there any questions on multi-dimensional linear regression? Okay. So the last part of this lecture, we're going to cover just a small common trick people use. So all of our regression has been linear so far. That is, it always is like a coefficient times a dimension. But there's one trick we can use to convert nonlinear problems into multiple dimensional problems. So let's say that you want to fit a parabola. So you want to have an x squared plus x plus, 1 kind of equation. So you want to fit a parabola. So if you look at the coefficients here, so it's going to be y equals beta naught plus beta 1x plus beta 2x squared. You can convert that into a multi-dimensional problem where your first dimension is 1s, your second dimension is x's, and your third dimension is x squared. So although this is a one-dimensional problem, there's only one x, you can view it as a linear three-dimensional problem. So this is a non-linear one-dimensional problem. You can convert it into a linear three-dimensional problem where you have a 1, an x, and an x squared. So for example, if your x was 2, your first dimension would be 4, your second dimension would be 2, and your third dimension would be 1. Okay, so notice this only works for polynomials. Okay, that's not true. It works for a couple. If it's it's a linear sum of nonlinear terms, it can work. So it could work if you had like sine of x here and maybe a plus cosine of x plus tangent of x, right? So you could do a bunch of functions here. But if you had something like, x to the beta, then that would not work. Okay, so it works for a sum of nonlinear terms, but it doesn't work for sort of, if you had maybe a log base beta times x or something. Okay, so we can convert this into a X matrix. So let's see an example. So this is just me generating the data. Don't pay attention to that. Okay. So here is the data. Okay, so it's a polynomial. Okay, and I've just showed you like the exact solution. That's just what it was if I knew what it was. Okay, so here I am making my X matrix. So I have here my X squared term, my X term, and my 1s. So it's one dimensional, but now notice that I have, these dimensions here. Okay, so here I am computing my betas. Notice it's just one line of code. And then here are my fit coefficients. So my x squared term is 2, my x term is minus 2.9, and my beta naught, my intercept is 4.2. And here I'm plotting it. So I did xmat, the X matrix times my coefficients. And so you can see in green, this is my fit. And you can see the fit is actually quite good. Okay. So that's all there is to it. So basically I just did, I converted it into a three-dimensional problem, and I was able to fit the polynomial quite nicely. Are there any questions on this example of linearizing a one-dimensional system to make a linear multi-dimensional system? Great. Okay. I'm just going to quickly go through this, but this is an example of the error analysis for that problem. Basically, it just shows you how to go through the error analysis, and I'm not going to go through it here, but This is just showing you that you can compute confidence intervals for your betas. So it's exactly the same thing we had before, but what we're doing is computing confidence intervals. Now, one thing I want to mention here is that although it was a one-dimensional problem, right, we're still fitting 3 coefficients. So it's still the n minus d, it's still n minus 3, right? So even though the problem was one-dimensional, we still are fitting 3 coefficients, so the degrees of freedom is still n minus 3. And then this is just me going through the error analysis, so I won't go into it in too much depth. And then we can still compute goodness of fit. Okay. So to summarize, if we're looking at a regression, we can justify a regression by doing a Spearman correlation test if it's one-dimensional. We can do a Shapiro-Wilk test on normality on the residuals, and that works in any dimensions. We can compute goodness of fit. And that basically allows you to assess a regression. If you want to justify like a model, like let's say that you want to know whether or not I should have an intercept or not, you can assess it by plotting it, right? And then you can do hypothesis tests on individual coefficients. Like you can do a hypothesis test to justify the intercept or the slope. Now, one thing is that you can't use goodness of fit to compare like whether or not an intercept is necessary. So like if you add an intercept, you always improve your goodness of fit. So it's never a valid way to justify an intercept or a slope or something like that. Okay, so these are the 2 ways you can say, hey, you know, this needs, like maybe that polynomial example, you weren't sure if you needed the x squared term. You could evaluate that by using a hypothesis test or by plotting it with and without an x squared term in the regression. Okay. So to summarize, if you want to do a regression, the first thing you would do is justify a regression is needed. So one way to do this is to plot it and show that, you know, the x and y look related, or you could use a Spearman correlation test. Then you compute your model coefficients, their standard errors, and report their confidence intervals, and you can report their p-values for existing. Okay, so, you know, justify that your slope and intercept are necessary, compute your confidence intervals. You don't always have to compute p-values. This is maybe only if you're unsure about them, but it's always good to have your confidence intervals for the model coefficients. Then you can plot your regressed model. Always want to plot your regression. And if you have n dimensions, you can use y minus your y versus y hat. And then once you have your model, you can compute your residuals and you can histogram them and compute Shapiro-Wilks on them. Now, this is a very thorough job. You know, I think in general, plotting it is key. Getting confidence intervals are key. And you can do the extra steps of the normality test and the p-values for existing if the regression maybe is not completely clear from the plot. Like if the plot doesn't look great, you know, you can do your test to make sure it looks good and your p-values. Okay. So that covers one-dimensional and n-dimensional linear regression and how to linearize nonlinear regression. Are there any questions?
Yeah, I have a quick question.
Yeah.
Will we be looking at, because I know my calculator, my handheld calculator can do other types of regressions like quadratic regressions and applying different functions to data. Will we be looking at that as well in Python, or is it just going to be linear regressions?
So like if you do quadratic regression or you're doing log regression, most calculators and most of the time what they do is they linearize it. So like let's say you want to fit like y equals log of x. Most of the time you just make log of x be it's a linear regression where you have log of x being the dimension. So most of regression you'll see is usually linearized. However, we will cover nonlinear regression, where you are in problems and you have to use nonlinear regression. So we will cover that. So that's arbitrary functional form. So that could be something like a tangent, a sine, a product of 2 dimensions, an x to the beta, any kind of arbitrary function. So we'll cover that in the next lecture.
Thanks.
Yep. Any other questions? Okay, so I will stop the recording then.